So I'm Niccolò Somaschi. I'm a co-founder, chairman, and CTO of Quandela. And today I'm going to tell you our approach to deliver photonic-based quantum computers. Quandela was created in 2017 by three co-founders as a spin-off from a CNRS center near Paris. We are now more than 60 people, 67 today. And we provide full-stack photonic quantum computing solution based on photonics. And among the experts, among the teams, we have expertise in semiconductor fabrication, quantum information theory, up to computer science, and of course, optics and engineering. We are based in Paris, in the south suburbs. We also have a branch, a subsidiary in Munich, and offices in Italy and Spain. And before going into detail, I want to zoom out and have a little review of the many approaches we can take to develop quantum computers. We can simply divide it into two parts, the matter-based qubit and the photonic qubits, which are conceptually very different and today not yet understood by the majority of the quantum computing community. So the matter-based qubit says the word, they are objects, they take space in a ultra-high vacuum, or they sit on a chip at very low temperature. They take space and they fill the environment. And the coherence is the error that forces limits the quantum computation. But as they fill the environment, they also fill themselves very well. So we can fabricate entanglement very efficiently. We can do logic gates in a deterministic way. But the challenge is to scale the manufacturability and the error correction. They are limited to the nature of this element. We have to fabricate millions of qubits with machines that are not able yet to do such a large-scale fabrication. We have to fabricate them perfectly to reduce the decoherence, and we have to find a way to connect them efficiently because they're limited by their topology. The photonic qubits are totally different because they don't sit in any chip. They fly through a processor, through optical fiber, or other classical elements. And they can manipulate it, therefore, very easily with the technology we can take from a telecom industry, fiber, integrated photonic circuit, and so on. But if we use this classical technology to do entangling gates and to generate photons, this comes at a very high price because all these processes, they are probabilistic. There is nowadays technologies to generate photon with 1% probability maximum, and the entangling gates, they have less than 50% probability, which means that when we need to entangle many qubits, we have to sum up very low probabilities, and we end up with a large, gigantic number of resources to develop this. In Quandela, we take the best of both worlds because we manipulate photonic qubits. So we develop photonic quantum computers using integrated photonic circuit, electro-optical elements, and optical fibers, but we do the generation of the qubit and most of the entanglement with a matter-based object. And we use 3-5 semiconductors, quantum dots, which behaves as artificial atoms, and they can generate deterministically one photon per time. And we can also entangle them in a deterministic way.
Can you say which temperature? The photon generation?
4 Kelvin. The platform then looks like this. Let's focus on the 3 blocks. So we need to generate qubits. We need to manipulate them and detect them. And detect them means measurement. And that's how we compute them. And the choice is done in Quandela consists in choosing the best technology to reduce all the losses that are required to reach the threshold for error correction. We start with superconducting nanowire detector, demonstrated efficiency more than 99%, low loss waveguide, as was presented before, and of course, our single photon generator and tangled photon generation. 96% is a theoretical value you can get from this paper. It gives you the recipe of how to fabricate these devices, which are based on our geometry. So it's the engineering effort that we are focusing on, and the purity as well that comes together with the fidelity of the logic gates we develop has been already demonstrated to be above 99% by the funding team in 2016. If we want to scale that, we don't need to manipulate single photon. We want to manipulate large sets of entangled photon, cluster states, following the very famous measurement-based quantum computing protocol. There we have a cluster state, many entangled photon, which are prepared offline, and we use single qubit measurement to perform the computation. This means that we have to start from linear small clusters, entangle them, and then work on a 2D graph in a space-time block, as you see there, 2D, and the third dimension is time. And the most used approaches today are based on the classical elements. I can generate single photon and entangle them probabilistically, which forces a gigantic effort with the best foundries in the world, with not standard components, and placing them together, and the resources just to generate this linear cluster state becomes huge, becomes the size of a full 300 millimeter inch wafer. And our approach, again, is to use the same device. Now we include a spin in the artificial atom, and by a standard protocol already proposed in early 2013, we can entangle each emitted photon with the spin in the atom, and therefore create a linear chain of entangled photon in a linear 1D cluster. So we can reduce the overhead, we can scale the quality, and we can scale the manufacturability. And this has been demonstrated this year by the team. You can find the details here of the paper. And we demonstrate we can generate 2 entangled photon and 3 entangled photon in a linear cluster state with 100 times higher and 10 times higher generation efficiency than other technologies. What's the limiting factor is the spin coherence time. Is an atom, we fight with coherence, but starting from a very low level today, 3 nanoseconds, we are already pushing it to tens of nanoseconds. And this means that we can include at very high speed the generation of more photons and get up to more than 5 or 10 photon in a linear cluster state. So today, we already develop and deliver full stack photonic quantum computers. We work on the full stack up to the cloud for an user interface. These are the stack. No surprise there. The technology I've mentioned before, I want just to mention that we also have a proprietary simulator, which is not only a linear optical circuit simulator for noisy circuits, and from 2023 also for cluster state manipulation, but is also the operating system. And this is the connector to HPC computing, to other connectors like Qiskit, Ticket from Cambridge Quantum Computer, already integrated, and from early next year to Atos machine. This is the system you see is designed to be modular, so it can be upgraded very efficiently and integrated in non-laboratory environment. We are also the first quantum computing company providing services on the cloud in Europe. We are the second if we consider UK. So we are the second, let's say. What you can get today in the beta version, so it's free until January, at the website you can see here, is the access to the simulator and to 2 QPUs. One for generating certified quantum random numbers, and the other with 5 qubits to be upgraded to 6, and to more than 10 middle next year. You can get your credits. You work in Python today. We will add notebooks so you can already take the product and the algorithm we develop and run them directly. We work already with industries. We are very focused in developing in industry and real useful use cases. These are the main areas we work on: cybersecurity, with cloud providers to secure the data center with certified quantum random number generator. It's an application that runs on a 2-qubit system and can be installed on premise because it's very compact. We work on molecular design, logistic, and this is the work we start to do with Thales on drone cohort flight and planning, and also with some finance-related companies. To focus on 2 use cases, I want to mention the work with EDF, which is the electricity provider of France, and Onera, to use partial differential equation solvers, which is developed internally in our team, to predict dam issues. And that can be, of course, used also in pipes and nuclear plants to define at which level of stress we have damage and therefore high risk. So it's a very important use case, and we are working on scaling it up to have a speed up compared to the classical approaches. And another, as was mentioned before, we also work very much with quantum machine learning, and within BDA was focused on using a hybrid system, classical machine learning neural networks together with the quantum part to classify polymers with respect to their aging properties. Just a bonus slide, photonics is cool, we know, but it also provides a path to an advantage if you look at quantum machine learning application. Why? Because the space that we exploit, the Fock space of the photons, is larger than the Hilbert space of the gate-based model. We can have 2 photons in one mode, but we cannot have in a gate-based model 2 qubits in one mode. So we can use this thing and realize that with the same number of qubits, the quantum computing space gets twice larger. So the effort on the technology to reach an advantage quantum computing on a speed up on a calculation can be achieved when things are done properly with less number of qubits. Take home message. So Quandela provides full stack quantum computing based on photonics, cloud access, and machine ready to be deployed and provide on premise. We already work with industry for state-of-the-art algorithms, and we work on the building blocks already demonstrated for scaling towards large machine and error correcting. I leave you with a slide with the publication that we put out on archive, some of them. There are 3 more that didn't fit in the slide this year. So we're very focused on the scientific validation of everything we provide on every part, from the algorithm to the hardware. Thank you very much.